In this video, we're going to discuss Hess's law. And what Hess's law is it allows us, it's a law that allows us to calculate the enthalpy change for reactions, right? It aids us in calculating the enthalpy changes for chemical reactions. And basically what Hess's law says is that the enthalpy change for a chemical reaction will be the exact same whether it occurs in one step or a series of steps, right? So to illustrate this, let's look at an example. So that example I want to look at is the combustion of methane, right? So we have CH4 reacting with O2 to produce carbon dioxide and water, right? So the enthalpy associated with this reaction is negative 890 kilojoules, right? That's if this combustion happens directly. But imagine that we have a series of steps. Let's say this happens in a two-step process. And in that two-step process, you go through an intermediate step where you create carbon monoxide gas, water vapor, and oxygen. And then those react to form carbon dioxide and water, right? So let's say instead of going directly to the final combustion products, you go through this intermediate. Well, Hess's law says that the total enthalpy change should be exactly the same. So I've written out this two-step process here. And we can show that this gives us the same products by looking at the net reaction. And basically, if you want to get the net reaction, you cancel out anything that appears as a product and a reactant in the two-step process, right? So carbon monoxide is produced here, but it's consumed in step 2. So we cancel that guy out. Same thing with the water, right? It's produced here, but consumed in the second step, right? So cancel out that guy. And then same thing with oxygen here. It's produced here, but consumed in that second step. So we do end up with the same net reaction. We have CH4 plus 2O2 yields CO2 and water. Right, now there's an enthalpy change associated with each one of these steps. The first step has an enthalpy change of negative 607 kilojoules. The second step has an enthalpy change of negative 283 kilojoules, right? What Hess's law allows us to do is to be able to sum up those enthalpy changes in order to solve for the total enthalpy change throughout the reaction. So the enthalpy of the reaction is going to be equal to the enthalpy change of the first step plus the enthalpy change in the second step, right? We just have 2 steps here. If you had 5 steps, you would have 5 different enthalpies, right? However many steps you have, you can just add those up to get the enthalpy for the total reaction, right? So we got negative 607 kilojoules plus or minus, right? Since we got a negative here, negative 283 kilojoules. And so that's going to give us negative 890 kilojoules. And if you notice, right, that is exactly the same enthalpy change for if this process happens in one step, right? We get the exact same enthalpy change even if we have it in a 2-step process. So why is this law valid, right? It's valid because enthalpy is a state function. If you remember from the first video in this unit, a state function, it doesn't matter what pathway you take, it's going to be the exact same, right? So we used elevation change as the analogy in that first video, right? So this is similar to elevation change. It doesn't matter what path you take to get there, as long as you have the same products and reactants, right? Which we do here in this 2-step process, same products and reactants, you're starting and ending at the same spot, then the total enthalpy released should be exactly the same. This is the fundamental basis of Hess's law. Now, there are 2 characteristics of total enthalpy change that are a product of it being a state function that we need to be familiar with. The first is that if we reverse the reaction, we also must reverse the sign of delta H. So for this example, I'm using the reaction of xenon gas with fluorine in order to produce xenon tetrafluoride as a solid, right? This reaction has an enthalpy change of negative 251 kilojoules, right? So let's imagine that we consider the opposite process. Instead of forming xenon tetrafluoride, we're going to look at the decomposition of xenon tetrafluoride into xenon gas and fluorine. If we look at that opposite process, it's going to have the same energy change associated with it. We're just going to flip the sign. So the enthalpy change associated with this process is going to be positive 251 kilojoules. Right? So if you reverse the reaction, you reverse the sign. The formation of xenon tetrafluoride should have the same magnitude of energy change as the decomposition of xenon tetrafluoride, right? It's just the sign is going to change, right? You think about it, it's the same bonds that are being broken, the same bonds being formed, so it's going to be similar energy requirements, or the exact same energy requirements to break versus forming these bonds, right? So that's the first thing you need to realize. If the reaction is reversed, sign is reversed. Be familiar with that characteristic of delta H. The second characteristic of delta H that you should be familiar with is that the magnitude of delta H is directly proportional to the amount of reactants and products. So let's say we take this same reaction and we double everything, right? We double the amount of xenon gas, we double the amount of fluorine. We're going to produce twice the amount of xenon tetrafluoride, right? So that means delta H, if we double everything, we're also going to release twice the amount of heat as well, right? So we're going to have 2 times negative 251 kilojoules. And so that's going to give us a delta H of negative 502 kilojoules, right? We just multiplied it by 2, right? So if you double the amount that you have, you're going to double the amount of heat that's released. If you triple it, you triple the amount of heat released, right? Et cetera, et cetera. Basically, these are 2 characteristics that you need to be familiar with for delta H so that we'll be able to use enthalpies correctly and that we're getting the correct numbers and signs, right? Okay, so let's put this stuff to the test. Let's go through an example. So an application of Hess's law. So this question says that the enthalpy of combustion for solid carbon to form carbon dioxide is negative 393.7 kilojoules per mole. And the enthalpy of combustion for carbon monoxide to form carbon dioxide is negative 283.3 kilojoules per mole of carbon monoxide. Use this data to calculate delta H for the following reaction. We have solid carbon plus O2 to yield carbon monoxide, right? So let's think about what we've been given here, right? We've been given the enthalpy changes for 2 processes, right? The combustion of solid carbon and the combustion of carbon monoxide. So let's write out those processes and see what we can discern from there, right? So color here. So we got the first one, right? We got solid carbon plus O2, right? Remember, the combustion reaction is always just interacting with O2. Right? So solid plus O2 is going to form carbon dioxide, right? Gas. And this O2 should be a gas as well, right? So we were given the enthalpy of combustion for that process, and that enthalpy associated with it is going to be negative 393.7 kilojoules per mole, right? Okay, so the other process we were given the enthalpy for is the combustion of carbon monoxide. So let's write that one out as well. So CO gas, right, plus O2 is going to give us CO2 as well, right? Now, these were specifically given for 1 mole of carbon and carbon monoxide specifically. We're good here for the first reaction, but you'll notice that the second reaction is unbalanced. Now, the thing that we'll have to take into account here is that this was given to us for per mole of CO. So we have to keep carbon monoxide as 1 mole. So this is the only situation where it's okay to use these fractional stoichiometric coefficients. So I'm going to use 1/2 O2 here so that we keep 1 mole of CO. So now that I've written it in this fashion, it's balanced, and the enthalpy change is negative 283.3 kilojoules per mole. All right, perfect. So we have these 2 reactions, and we're trying to find the enthalpy for this specific reaction, right? So carbon solid plus O2 to form carbon monoxide, right? So in order to find this, we can use these two reactions. As long as our reactants and products are the same, then we'll have the same enthalpy change overall. We'll just have to add our two enthalpies for each individual reaction, right? So we can think of this reaction as a two-step process. So let's say we have two carbon solid plus O2, right? We can envision this forming carbon dioxide as an intermediate step, right? So we'll have two CO2, and then that carbon dioxide forms carbon monoxide. Right, so that's going to form carbon monoxide plus O2. Right, so considering this as a two-step process, so this is step one, this is step two. The reason why it's convenient for us to envision this as this two-step process is that we already have the enthalpies that we need in order to solve this problem. First, let's get the net reaction so that we can be sure that we have the same total reaction that we're looking for, right? So CO2 is going to cancel out here, right? And O2, oh, I forgot. One stoichiometric coefficient here. So this should be 2 O2, right? Yep, so that balances that. Right, so the CO2s cancel out there, and then this 1 mole of CO2 cancels with 1 mole this 1 mole of O2 cancels with 1 mole of O2 in the reactants here. So we end up with the following net reaction. So we'll have 2 carbon solid plus O2 yields 2 CO, right? So this is the same as the reaction that we're looking for, right? So each step, we actually already have the enthalpies necessary to solve for each of these steps, right? So this reaction is the same as this one, except everything's been multiplied by 2. So all we have to do is multiply this enthalpy by 2 in order to get the enthalpy for that reaction. So the enthalpy here is going to be equal to negative 787.4 kilojoules per mole. And that's just this enthalpy multiplied by 2, right? Since we multiplied everything by 2 here. And for the second step, it's the same as the combustion of carbon monoxide, except it's also everything multiplied by 2, and we reverse the products and the reactants, right? In the combustion of carbon monoxide, CO2 is a product. Here, CO2 is a reactant. So we reverse the sign and we multiply by 2. That's going to give us a positive 566.6 kilojoules per mole, right? So basically all I did was take this value, change the sign, and multiply by 2. So now in order to solve for the enthalpy, right? So I'll call this one delta H1 and this one delta H2. To solve for the enthalpy of the reaction, right? All I got to do is take delta H1 plus delta H2 by Hess's law, right? So when you add both of those together, you get negative 220.8 kilojoules per mole. And so that gives us the enthalpy of this reaction, right? And we were able to solve for that because we were given enthalpies of combustion that gave us the enthalpies that we needed to just be able to solve for it through Hess's law.